Okay, this video is part of the calculus series and is for the parametric equations, polar coordinates, and vectors unit. This will be our introduction to parametric equations and plane curves. All right, let's start with this. We know how to find position and find a position equation from an acceleration equation if we have motion in one dimension. If it's just what we call projectile motion, where we just have gravity, maybe we're in the metric system, the acceleration as a function of time is negative 9.8 meters per second squared, where up is positive direction, so gravity is operating in the downward direction. We can derive the equations for the speed or the velocity of an object and the position of an object by knowing that the derivative of position is velocity and the derivative of velocity is acceleration. So to go from acceleration to velocity, we have to take the antiderivative. That will leave us with a constant here, and if we have a known velocity at a known time, we can establish that. Often it's the initial velocity. And then if you do the integration again, you get the position equation, which has its own integration constant. Right? And that's really good for modeling motion in a single dimension if the motion stays only in one direction. There's one output, which is the position, or the input of these functions is time, and the output is position, so it's one-dimensional. But what if we wanted to model an object that's launched in such a way that it follows a two-dimensional path like this? Like maybe we launch it and gravity acts on it, and then it causes it to slow down and then finally hit the ground again. Well, we could just map that course out, right? Figure out what the vertex is here. That's at 40, 0, and start building a conic section to match that. Now that we know that, this is an x squared type, so it'd be x minus 40 squared equals some 4p times y minus 100. And if we want to launch it from the ground at time 0 here, we can make sure this goes through the point 0, 0 by plugging that in and solving for p. P ends up being negative 4. So now we have this standard equation, and if you end up solving this for the y, you end up getting y is negative 1/16 x squared plus 5x. And we could even graph that, use our technology if we happen to have a calculator and we're allowed to use a calculator. Maybe we could plug that equation in, take our calculator and go to y equals and enter negative 1/16 times x squared plus 5x. And then we could graph that. A good window to use here would be from 0 to 80 in the x and from 0 to 100 in the y. And then if we graph that, we'll see the path where we're plotting x and y. So here's that parabolic path there. Okay, now this is good to get a picture of the path of the object, but it doesn't really give us a good sense of where the object is at any particular time, right? So, maybe we could do better than that, and that's what we're going to study next. Since this motion is in 2D, we have x and y, but both of those quantities are varying with respect to a third variable, which is time in this case, t. And so instead of representing the curve as y as a function of x, we can change this to be x and y both as a function of this new variable called the parameter, which in this case is time. Since it is time most frequently, we usually use the letter t for this parameter. So instead of having, like in this equation here, we have y as a function of x. Now we're going to have a set of equations which are called parametric equations, and we're going to represent x and y both as functions of a third variable t, and that t is called the parameter. Right, now one way to do this is to say, if gravity is operating in this direction, then once this ball is in motion, there's nothing causing it to change its horizontal motion. It's just going to keep moving steadily in that direction. So we could just say x is equal to t. Maybe it turns out that, at 20 seconds into the flight, this is 20 feet over to the left, and then 40 seconds, and so on. That would make this equation for x equals t. And then the y would go up and down according to our graph. Y is negative 1/16 t squared minus 15t. Right? So this is like the same equation. We've just decided to write x and y separately as functions of a new equation. Didn't buy us much in this case because they're exactly the same, but you can get the idea. The idea is to separate x and y and have them each be a function of this third variable t. That's the concept of parametric equations. All right, so then we could do things like this. We could say, first, it might be helpful to know what ranges of the parameter t can take to describe the full object's path. So the object starts when y is 0 here at the ground, and it ends its flight when y is 0 again. So we could take the y parametric equation here, this one, and force this side to be 0 and find out the times when it is 0. So if I said y equals 0, you can factor a t out, and that means that either t is 0 or this is 0, which occurs when t is 80. And so that means that we'll be at y at 0 when the parameter t equals 0, when time is 0, and we'll be back at y at 0 again when the parameter t is at 80. Maybe it's 80 seconds, something like that. All right? Yeah, so you can just plug in different times here and find out what the x and y are, right? So for example, I could take my calculator and I could plug in a particular time value, and that time value happens to be also the x coordinate. So if I wanted to know, what, let me go to a table here, and maybe I can change this to ask, and then go over here and say, all right, what if I want to know where the object is at time 10 seconds? So if I go to 10 seconds here and hit enter, then this y tells me that that particular time, the x coordinate of that point is 10, and the y coordinate of that point is 43.75. Or if I want to know, what's happening at time is 72 seconds or something like that, I can type in that parameter here, right? And the x is 72, but the height is 36. The idea being you can plug in any time into these two equations and find the x and the y coordinates. So now we have two-dimensional information versus time. All right, so this could be could apply to any curve, not just physics curves. Let's say that I have a more interesting equation like this that has x and y as a function of time, and this time x is not just equal to t. X is t squared minus 4, and y is 1/2 t. And t is going to be defined from -2 to 3. So maybe this t represents time, maybe it represents something else, we don't know. But one thing we could do is we could just pick some values of t between -2 and 3, plug those into the equations for x and y, and find the x and y. So when t is -2, this equation is -2 squared minus 4, which is 4 minus 4, which is 0. So the x coordinate is 0. And when t is -2, the y location is 1/2 times -2, right, which is, let's see, -2 times 1/2 would be -1. So actually this is incorrect. This is a -1 right there. And that means if we wanted to graph that, we could go ahead and graph this. I'm going to graph on the xy plane. What I'm finding is at t is -2, the x is 0, and the y is -1. So I am currently right here at this location at the time t is -2. All right, then I can go to another place. I could say, all right, what happens when t is -1? So if I wanted to know that, I could plug -1 in for time to these x and y equations. So let's do that. If I plug -1 in here, this is -1 squared minus 4, which is 1 minus 4, which is -3. So the x coordinate is -3, and this would be 1/2 times -1, which would be -1/2. So I would be at the location, let me put some tick marks on here. 1, 2, 3, 1, 2, 3, 4. Okay, so I would be at the location -3, -1, 2, 3, -1/2. That's right. Sure, my notes here. Yeah, I would be at -3, -1/2, so right at this location when I'm at t is -1. Okay, and I can continue doing this. Now this is a little tedious, but I'm going to do a few more just so we can get the idea. And if you didn't have a calculator, you might have to do a curve this way. You'd have to try plugging in individual values. So what about when t is 0? T is 0 would be -4 here and 0 here. So that means we would be at the location x is -4, y is 0, when t equals, let's see, 0. And then at 1, you'd get the location -3, 1/2. So -3, 1/2 would be here. And that's when t equals 1. And then, let's see, when you plug 2 into the equation, you get 0, 1. So that's here when t equals 2. And then if you plug in 3, you get 5 for x, 1, 2, 3, 4, 5, and 3 halves, which is 1.5 for y, when t equals 3. Okay, so then if I were to draw a curve in there, right, this curve goes like this, goes through those points, right? And not only that, but it goes in a particular direction. So whenever you graph a curve of a parametric equation, it's called a plane curve, and it has a direction because you have to add an arrow, at least one arrow, that shows the direction that we're moving as the parameter goes from lower values to higher values. So as this t parameter, in this case time maybe, goes from -2 through 0 up here to +3, right, the object is moving specifically along that path. All right, so kind of tedious to graph by hand, but you could always graph that by hand by making a table. It'll have 3 columns. The first one will be the parameter value, t, and then we'll plug that into the x and y. Okay, now if you are allowed to use a calculator, then there's a nice feature in your calculator that allows you to graph this more quickly. So if you take a calculator and you go to the mode button, the 4th line down here has, by default, it comes up FUNC. That means the calculator is in functional mode. But the second mode over here, PAR, stands for parametric mode. So if you click that and hit enter, that changes the way graphing works. So if I go to y equals, instead of getting y1, what I have is x and y for curve 1 in terms of parameter t. And that means that I can enter separate equations for x and y. And when I use the variable button here, it's going to show up as a t. So t squared, I'm going to enter this set right here, t squared minus 4 for the x as a function of t, and then 1/2 t, 1/2 times the variable key for the y equation. So if you enter that, then what you can do is, let's go ahead and just say zoom 6, which is origin plus or minus 10. You'll see a part of a curve there. We definitely want to go to the window. Now the window, it gives you x min, x max, and x scale, and y min, y max, and y scale. But at the top, it gives you t min, t max, and t step. So this is the parameter. By default, this comes up with sketching from 0 to 2 pi, which is 6.23. So if I wanted this to sketch from -2 for the parameter to 3 to match our sketch, I would have to change the minimum and the maximum. And then also, I'm going to zoom in a little bit and just make this x and y just be plus and minus 4, let's say, or let's do 5. So -5 to 5 in the x. And then I'm going to scroll down further and make the y limits -5 and 5 on the window. And then when I hit graph, I should get something that looks a lot like our curve there, right? All right, so that's how you can force a calculator to graph that. Now, if you can watch it graph, then you can see that it traced out that graph specifically in that direction, right? But if not, you'd have to build at least 2 points on this table to see what direction you're moving by noting the parameter values at a couple points, so you could add a direction arrow onto the graph. This is really helpful to be able to specialize, to kind of predict these curves and to graph these curves. So that's parametric mode. Okay. All right. Another way that is helpful to graph when we don't have a calculator is to try to convert these parametric equations back into a standard, what we call rectangular form, where y is a function of x. And we do that by eliminating the parameter. So the way that works is you take a set of equations. Say we've got this right here, t squared minus 4 1/2 t. That's the same problem we just did. We could solve one of these for the parameter t, like this one. If y is 1/2 t, multiplying both sides by y means t is, or by 2, is t is 2y. And then I could substitute that in this. So x would be that t of 2y squared minus 4, which means x would be 4y squared minus 4, which means, let's see, that I've got, let's see, now looking at this, we could use our knowledge of graphing conic sections. This is a conic section. It's going to be a parabola. It's y squared type, so it's going to open up left or right, and we can put it in standard form. So what I could do is move the 4y to the other side. So this is 4y squared is, let's see, x plus 4 if I add this to the other side and swap, right? And then you could think of this as 4y minus 0 squared equals x plus 4, which means the vertex of this parabola would be at negative 4, 0. So if I wanted to sketch this, I could go to, let's see, negative 4, 0, and locate one place on there. And then I know that this value here, this 4, let's see, I got to divide it to the other side. Actually, to put it in standard form, it's y minus 0 squared equals 1/4 x plus 4. And 4p is equal to that 1/4, which means p would be 1/16, right? P would be 1/16. And that means that we would go from here. Now it's going to be hard to sketch this way, but you could go 1/16 this direction, right? 1/16 this direction, and then twice that much in this direction and this direction to get the other two spots. So we could graph the parabola like this. So we know it's that shape, right? And then to figure out the direction, we could make a table where we have t and x and y, and just pick at least two values to see the direction. So maybe I could do this. I could say, let's try 0. And if you plug 0 in here, you get 0 squared minus 4, which is negative 4 for x. If I plug a 0 in here, I can get 0. So that means we're at the point negative 4, 0. We're there at t equals 0. And then maybe I could try t equals 2, let's say. So 2 would be 2 squared minus 4 would be x is 0. And a half of 2 would be 1. So we're at the point 0, 1. Let's see when we're at t equals 2. So from that, I can tell that I've got to put my arrow in this direction. Okay, so this is another way to graph quickly without having to do the whole thing in a table. You can get the curve shape from eliminating the parameter and graphing with our knowledge of conic sections, because often these will turn into conic sections. Okay, here's another example. Let's take a look at this. We could maybe try to do that elimination of the parameter. So we'll solve one of these. Let's see, if x is equal to 2t, then that means t is equal to 1/2 x. And I can substitute that back in here. Y equals 4 times 1/2 x plus 3, which is y equals 2x plus 3, which isn't a conic section, it's just a line. So that's easy to graph. We have a y-intercept of 3. And we have a slope of 2, which means we go over 1 but up 2. Up 2 over 1. That means the curve is this, right? So now I have the shape. And to get the direction, we'll make a little table here and plug in two values for t. Let's plug in 0 and 1. So if I plug in 0, x would be 0. Y would be 3. So I'm at 0, 3 at t equals 0. And then if I plug in 1, x would be 2. And y would be 7. So we're at 2, let's see, 2 and 7 somewhere over here at t equals 1. So that means that we have to add our arrows this direction. All right, so plane curves for parametric equations must contain direction arrows. Okay, what about this? Another way that we sometimes can work is, here we've got cosines. Now, we could try to solve this for t, but then we're going to end up with, well, let me show you this. This is actually the wrong way to do the problem, but if you use the same idea, you would maybe say, let's take this one and solve for t. So that means 2 cosine of t equals x minus 1. So cosine of t is x minus 1 over 2. So then that means t is the inverse cosine of x minus 1 over 2. And then you can plug it into the other one. Y is negative 2 plus 3 times the sine of the inverse cosine of x minus 1 over 2. So that's what we just described. Solve for t, plug it in. But unfortunately, this is not easy to graph, right? It's very difficult to figure this out. So that's not particularly helpful. Instead, we're going to take advantage of a trig identity for this. The ones that we used when we did trig integrals, the Pythagorean identity, we know that cosine squared of anything plus sine squared of anything is always equal to 1, right? So if I can independently solve these things for cosines and sines, I can plug those into this equation and eliminate the t that way. So this first equation can be solved. This is 2 cosine t is x minus 1. So cosine t is x minus 1 over 2. That's this equation. And this equation can be solved also. 3 sine of t is equal to y plus 2. So sine of t is equal to y plus 2 over 3. Then what we're going to do is we're going to put those two things into the Pythagorean identity. So if cosine is replaceable with x minus 1 over 2, and that's squared, and then sine is y plus 2 over 3, and that's squared, equals 1, that gives me a way to eliminate the t's and rewrite it in terms of x's and y's. Now, since this is squared, I could write this as x minus 1 squared over 2 squared, which is 4. And this is y plus 2 squared over 3 squared, which is 9. And we recognize that as an ellipse, which means we could graph this by using the center, which would be at 1, negative 2, right? And then we could go over, this is 2 squared, so we would go 2 in the x direction. And we would go, let's see, that's 9, so 3 in the y direction. And then draw our ellipse in like this. Right? So this is a quick way to graph. Right? This is the parametric equation for an ellipse, not centered at the origin. Right now, to figure out the direction, we're going to have to make a little table. We've got x, y for different t values. And maybe I could pick like 0 and pi over 2, because those are convenient to use with sines and cosines. Right? This would be 1 plus 2 times the cosine of 0, which is 1, so that is 3. And this would be negative 2 plus 3 times the sine of 0, which is 0, so that would be negative 2. So that means we're at the location x is 3, y is negative 2, which is right there at t equals 0. And if I try pi over 2, then that means these equations would be, let's see, 1, x is 1 plus 2 times the cosine of pi over 2, which is 0. So that would be 1 for x. And negative 2 plus 3 times sine of pi over 2 is 1. That would be 1 for y. So we're at the location 1, 1, which is here when t equals pi over 2. And that means that we have to add our direction arrows this way, because we're going this way around the curve. All right, so that is a parametric equation, plane curve with direction arrows for this particular parametric set of equations. Okay, now we should always specify what the range is of the parameter that we need for the part of that plane curve that we need. So if we only need this to go around once, that means the t parameter would only have to go from 0 to 2 pi, and it would traverse the entire section. Right? And that would result in limits of x and y. So x would stay between negative 1 and 3, and y would stay between negative 5 and 1. But we really shouldn't call these domain and range, because it's not really a function. It's not defined that way. Okay, so another thing to know is that these parameterizations, they're not unique. You can come up with multiple different ways to parameterize most curves. The most common way to parameterize is just to make one of the variables the parameter itself. So like just replace the x's with the parameter t and then write out the entire curve. So if, let's say you have this y is a natural log of the quantity 2x plus 3 squared, you could just make this the parameter. And then that means y is the exact same thing, it's just we're using the parameter instead of x. Right, but we could also do this. We could say, what if we wanted to make this whole thing the parameter t? Then this would become y is natural log of t squared. That would be the parametric equation for that. And then the x would be, you would have to take this, that t is equal to 2x plus 3 and solve it for what x is and make that the x equation. So both of these parameterizations are equally valid to cover this function. If you graph them, they have the same curve shape. It's just that I recognize that you might need to use different ranges of t to get different parts of the curve. So for example, if we just had t go from negative 10 to 10, it would graph more of the curve if we had this parameterization and less of the curve if you had this parameterization. Right? But parameterizations are not unique, so there's more than one correct way to parameterize a curve. Okay, the two most common parameterizations are just to make one of the variables the parameter itself and just replace it in the other one. We use those for more complicated situations. And then the other one that comes up quite a bit is that example that we did back here where we used the Pythagorean identity to parameterize. That one comes up whenever we have kind of ellipses or circular shapes. So those come up frequently as well. And you can use any letter for the parameter. It doesn't have to be t. If you're more comfortable thinking of it as an angle and calling it theta, you're welcome to do that as the parameter, right? It's just that you end up with x and y as a function of some third variable. And that third variable is called the parameter. Okay, a few more examples here. Let's see, do I have more here? Yeah, I think at this stage, we've got all the basic ideas. So I'm going to end this video here, but I'll have a second video that covers additional examples.